All right, now that we've reviewed limits for functions of a real variable, we're going to talk about limits for functions of two variables. Everything we talk about is easily generalized to functions of several variables, but we're going to stick to two variables for concreteness. So let's get to it. What does it mean to say that the limit as xa goes to ab of f of xy, xy goes to ab of f of xy equals L? So xy are points that are approaching ab, and we want to say what it means for the values of the function f of xy to limit to L. So just as before, this should mean that f of xy is a good approximation to L if xy is close to ab. So again, we've got some it's a little wishy-washy, saying good approximation and close to AB. But let's try to make this more precise. So what does it mean to say that xy is close to AB? Well, we're measuring distance between xy and AB. So to say that it's close means that that distance is small. Again, we still have the ambiguity of what small means, but we know now that we're talking about distances. Another way to say the distance from AB to xy is the magnitude of the displacement vector. So let's think about the displacement from AB to xy, call that h. And to say that that xy is close to AB means that the magnitude of the displacement vector is small. So if the magnitude of the displacement vector is small, then we want to say that f of xy is a good approximation to L. So that means that the error in approximating L by f of AB displaced by h, so that's f of AB plus h, so we add the components of h to each of the coordinates to move by h, and we want to say that that error is small. Well, we still have the issue of what it means to be small, but we know how to handle that using epsilon and deltas. So given an epsilon, there exists delta, so that if the absolute value of h is less, or the magnitude of h is less than delta, then the error is less than epsilon. So epsilon here is representing how big we're going to allow the error to be, and we're going to say that the error is less than that number epsilon, so long as we don't move more than delta away from the point AB. All right, well, let's look at an example to see how this actually works. So here's an example. The claim is that the limit as xy goes to 0, 0 of x plus 3y is 0. So in order to see why this is true, we need to say that given an epsilon, we can make our error in approximating 0 by x plus 3y, we can make that error less than epsilon, provided we are displaced from 0, 0 by, at most, some number delta. So again, working backwards, we can find delta equals epsilon over 4 will work. Let's verify that, and we'll talk more about working backwards in a minute. So let's take our displacement vector h, h1, h2. That's our displacement from the origin, 0, 0. And we'll assume that that's less than this number delta that we wrote down, that distance to the origin. So what's our error? Well, we look at the value, that's 0, minus the limit that we're after, 0, minus the value of the function evaluated at displacing from 0 by h1, h2. So we're just plugging in h1 and h2 for x and y. That becomes h1 plus 3h2. And again, we're adding two numbers and taking the absolute value, so that's less than or equal to the sum of the absolute values. And now a claim that this is less than or equal to the magnitude of h plus 3 times the magnitude of h. So why is that? Well, if we think about what does it mean to say that h has magnitude less than delta, well, it means that that vector, this is the position vector of a point that lies inside the set of points in the plane, distance at most delta from the origin. So here's h, and it lies inside of this disk of radius delta. Well, it's pretty clear that h1, which is the distance to the y-axis, and h2, the distance to the x-axis, is less than the magnitude of h. This is this is also easy to derive analytically, but this nice picture sort of explains why this is true. Well, we've bounded h. That's what we that was our assumption, is that the magnitude of h is at most delta. So the magnitude of h plus 3 times the magnitude of h, that's 4 times the magnitude of h, which is therefore less than 4 delta, but delta was epsilon over 4, and so the error is at most epsilon. So how did we work backwards? Well, what we really did is we started with this error. We wrote down the error in terms of h. Let's say we didn't know what delta was yet. We write down the error, and then we start bounding that error as we did here. So up until this point, we didn't have to use the fact that the magnitude of h was less than delta. And what we see is that we're bounding the error in terms of the magnitude of h in some usable way. So whenever you can do that, then by bounding the magnitude of h, we end up bounding the error. So let's look at another example, which isn't so simple. So here's an example. Let's look at the limit as xy goes to 0, 0 of xy over the square root of x squared plus y squared. And the claim is that this is 0 again. So given epsilon, we need delta. So let's work backward now in the example explicitly to see how we can produce delta in the way that I described a moment ago. So let's work backward. So here's our displacement from the origin. So we take h, and we're trying to bound the error of approximating 0 by this function. So we write that down. The error in absolute value is at most the absolute value of the difference. The 0 goes away. We take the absolute value of this number. That's the absolute value of the numerator over the absolute value of the denominator. The denominator, though, is just the magnitude of the vector h. So what we get is that the error is just exactly given by the absolute value of the components, product of those components, over the magnitude of h. Well, as we saw previously, this absolute value of h1 and absolute value of h2 are bounded above by the magnitude of h. And so the numerator is bounded above by the product of the magnitudes. So h1 absolute value is at most the magnitude of h, h2 is at most the magnitude of h, so their product is bounded above by the magnitude squared. Well, that's just the magnitude of h, and so all we need to do in this case then is let's just let delta equal epsilon. Because then, if we require that h is less than delta in absolute value, then this becomes less than delta, which is epsilon, and our error is at most epsilon. That's what we wanted.